procedures that we're using to design infinite impulse response filters rely on the availability of continuous time filter designs that then get transformed into discrete time filters. So we're basically converting from a differential equation for the continuous time system to a difference equation that describes the discrete time system. We're going to look at continuous time Chebyshev and elliptic filters in this lecture. We've already looked at the Butterworth filter. We saw that it was monotonic in both the pass and the stop bands. So for a low pass filter, the response monotonically decreased throughout the pass band and then on into the stop band. Now, there's two types of Chebyshev filters. The type 1 Chebyshev filter has ripple in the pass band, but then is monotonically decreasing in the stop band. In contrast, the type 2 Chebyshev filter is monotonic in the pass band, but then has ripple in the stop band. So we'll look at both of those in this lecture, and then we'll also briefly touch on the class of elliptic filters, which have ripple in both the pass and the stop bands. The advantage of adding ripple is that it allows for a narrower transition band for a given filter order. So for the Chebyshev type 1 filter, the magnitude response squared is given by this particular function. It's defined as 1 divided by 1 plus epsilon squared times Tn squared sub n of omega over omega naught. And Tn is the nth order Chebyshev polynomial. So from this description, we can discern the characteristics of the filter as well as its pole locations and zero locations. One observation about these Chebyshev polynomials is that if the argument is less than 1, then the polynomial oscillates between plus and minus 1, with a value of 1 being obtained at the argument of 1. In other words, when omega is equal to omega naught. So since this polynomial in the denominator is oscillating between plus and minus 1, then we know that the squaring that is going to mean it oscillates between 0 and 1, and thus we know that the magnitude response squared oscillates between 1 over 1 plus epsilon squared, which happens whenever t sub n is equal to plus or minus 1, and then 1 when t sub n squared is equal to 0. So if we sketch the magnitude response for this particular system in the pass band, we know that it's going to oscillate between a particular range. Then, when the argument of the Chebyshev polynomial is greater than 1, the polynomial is monotone increasing. So since we have a monotone increasing function in the denominator, when omega is greater than omega naught, we know that the magnitude response is going to be monotone decreasing. So we see that once we get greater than omega naught, the response is going to fall off, and that's what enables us to have a stop band for this particular filter. At DC, the magnitude response squared is either 1 when the polynomial order is odd, or it's 1 over 1 plus epsilon squared when the Chebyshev polynomial order is even. So these characteristics of the Chebyshev polynomial enable us to discern what sort of filter we're going to obtain when we build something of this form. Now this filter has 3 design parameters. We have n, epsilon squared, and omega naught that enter into determining the frequency response of the filter. So since we know that at omega equals omega naught, the magnitude squared is going to be 1 over 1 plus epsilon squared, then we can set the passband edge to be omega naught, because for omega greater than omega naught, we know the response is monotone decreasing. Once we do that, we can choose our epsilon squared parameter to obtain the desired degree of passband ripple tolerance. So if that's 1 minus delta P1, I'm going to choose epsilon squared so that 1 minus delta P1 is equal to the square root of 1 over 1 plus epsilon squared. And then finally, we'll choose the order of the filter, n, so that it satisfies the stop band constraint. At frequency omega sub s, which is our stop band, we want to have the magnitude response squared of the filter be less than delta sub s squared. And by increasing n, we get increasing levels of attenuation in the stop band. Now, it turns out that you can show that this particular filter has poles located on an ellipse in the S-plane. And from that information, we can discern where the poles should be once you specify n, epsilon squared, and omega naught. From those poles in the S-plane, we represent the transfer function of the system, which we're not going to do because it gets rather complicated. But nevertheless, it's easy to do with a computer, and many software packages already have that ability. Now, the Chebyshev type 2 filter also relies on a Chebyshev polynomial, but in this case, in the denominator of the frequency response magnitude squared, we have 1 in the numerator, and then we have 1 plus epsilon squared, the Chebyshev polynomial squared, of omega naught over omega, the whole thing inverse. So again, this relies on these Chebyshev polynomials. You can simplify this to write it in the form where you see that you have epsilon squared, the Chebyshev polynomial squared of omega naught divided by omega, and then in the denominator we have 1 plus epsilon squared, Chebyshev polynomial squared, omega naught over omega. By putting the polynomial as a function of omega naught over omega and putting omega in the denominator, we flip the pass and stop bands. So whereas in the type 1 filter we had ripple in the pass band, now because we have omega in the denominator, this argument of the Chebyshev polynomial is going to be less than 1 for frequencies greater than omega naught. And so when this argument is less than 1, the polynomial oscillates between plus or minus 1. Hence, we know that the magnitude response squared oscillates between 0 and epsilon squared over epsilon squared plus 1. So we know in the stop band we've got this kind of oscillation now. We know that as omega goes to 0, in other words, the argument of the Chebyshev polynomial goes to infinity, this polynomial is monotone increasing, so we get a larger and larger values here for Tn squared, and thus the 1 drops out, and basically our response converges to 1. But we see that it's monotone decreasing from DC on to where the edge of the stop band is. And furthermore, that at DC we have a gain of 1. So using these properties, we can, again, determine where the poles are for this particular filter and hence construct a system function. The algebra is kind of messy to do that, so we're not going to go through that. Finally, we'll conclude with a very brief overview of an elliptic filter. The magnitude response squared for those takes the form of 1 over 1 plus epsilon squared u sub n squared of omega, where u sub n of omega is a Jacobian elliptic function. With this particular function, we get equi-ripple error in both the pass and the stop bands. So this filter has ripple in the pass band and the stop band, whereas the Chebyshev filters had ripple in either the pass band for the type 1 or the stop band for the type 2. By allowing ripple in both the pass and the stop bands, we get the narrowest possible transition band for a given filter order and set of ripple specifications. So we have 4 different classes of continuous time filters that we can use to obtain discrete time filters. And of course, if the filters have these properties of monotonicity in a pass or a stop band, or ripple in a pass or a stop band, in the continuous time case, then the discrete time filters will have the same sorts of properties. The availability of these 4 classes of filters proves to be a very powerful tool for us then in designing discrete time filters.